power. Power is defined as work done per unit time. It is denoted by P. And power can also be measure how a man can do particular work in a good time. That is, greater will be the power. If we calculate the power at an instant time t, then we take small work done dw and small time interval dt. Then power is defined as P equals to dw upon dt. We know that work done is equal to dw equals to F into ds. We replace it by F into ds by dt. We know that ds over dt is equal to velocity. Then we put also P equals to F dot V. This is the dot product of two scalar quantities. That means power is also be a scalar quantity. When V is along force F, then we put theta equals to 0 degree. Then the power equals to Fv cos theta and F into V cos 0 degree. We know that cos 0 degree equals to 1. Then power is equals to Fv. Now the next topic is dimension of power. We know that power equals to work done upon time. Then we put the dimension of work done ml square t minus 2 upon times dimension t. Then the dimension of power is equals to ml square t minus 3. And the next topic is unit. What is the unit of power? We know that P equals to W upon T and work done equals to joule and time equals to second. That means joule per second, or it may be written as 1 watt equals to 1 joule per second. The another unit of power is watt, and the biggest unit of the power is 1 kilowatt is equal to 10 to the power 3 watt, and 1 megawatt is equal to 10 to the power 6 watt. Another unit of power is horsepower. Which is used in engineering. Its value is 1 horsepower is equal to 746 watt. We take some examples and calculate its average power. The next topic is average power consumption in daily activity. That is activity and average power. Firstly, we take breath, that is 1.2, sleeping, that is 25, slow walking, that is 200, and bicycling, that is 400. The next topic is potential energy. What is potential energy? The energy possessed by an object by virtue of its motion, that is called potential energy. This is basically two type of energy. First is gravitational potential energy, and second one is elastic potential energy. Here we firstly discuss gravitational potential energy. Energy possessed by virtue of their motion above the earth's surface, that is called gravitational potential energy. Its value is equal to mgh, where m is mass, g is gravity due to acceleration, and h is height. The next topic is elastic potential energy. For discussing this potential energy, we take another spring potential energy. The energy associated with the state of compression or expansion, that is called spring potential energy, and its value is kx. The next topic is Hooke's law. According to Hooke's law, the force is directly proportional to the stretch, where K is spring constant and F is force. Greater will be the stretch and greater will be the force. Next we take the example problem. The length of a steel wire increased by 0.5 centimeter when it is loaded with a weight of 5 kg. Calculate the force constant of the wire and work done in stretching the wire. Take G equals to 10 meter per second. Here x equals to 0.5 centimeter and m equals to 5 kg and G equals to 10 meter per second square. Then we firstly find out the force. F equals to mg, m equals to 5 and 10, force equals to 5 Newton. We know that K equals to F upon x, then 50 Newton upon 0.5 centimeter. Firstly we change 0.5 centimeter into meter. 50 Newton by 5 into 10 to the power minus 3 meter. Then K equals to 50 upon 5 into 10 to the power minus 3. That is, the answer will be 10 to the power 4. And secondly we calculate the work equals to half kx square. That is half into 10 to the power 4. 5 into 10 to the power minus 3 square. The answer will be 0.125 joule. Now we take the second problem is an elevator weighing 500 kg is to be lifted up to a constant velocity of 0.4 meter per second. What should be minimum horsepower of the motor to be used? Then problem second. M equals to 500 kg and V equals to 0.4 meter per second. Firstly we calculate power. M into V. Then the power equals to 1960 watt, and we know that 1 horsepower is equal to 746 watt. Then we change watt into horsepower. 1 watt equals to 1 upon 746 horsepower. Then 1960 watt is equals to 1960 upon 746 watt. The answer will be 2.6 horsepower. Now we take the next topic, conservation of energy. What is the statement of the conservation of energy? It means energy can neither be created nor be destroyed. It can only be transferred from one form to the another form. We take its example is a stone is held at a speed in the air, that is called the conservation of energy. And the total energy is constant in the system. The next topic is illustration of conservation of energy. We take 3 points, point A, point B and point C. This is the ground. This is X. Firstly, we calculate the energy at point A. At point A, in the air, the potential energy is mgh and its kinetic energy is 0. Then the total energy is potential energy plus kinetic energy, that will be mgh plus 0, that is E1 equals to mgh. Now we take the energy at point C. At C, firstly we calculate the V from the third equation of motion, v square minus u square equals to 2as. Here u square is 0, then we put 0, 2 into a into s is x, that is v square equals to 2ax. At point C, the potential energy is equals to 0 and the kinetic energy is half mv square. Half into m into, here v is 2a, x is equal to h at point C, that is half into m into 4ah, that is cancel out, the answer will be mgh, E2 equals to mgh. And at point B, firstly we calculate the V1. The answer will be V1 square minus 0 equals to 2ax. V1 square equals to 2ax and the kinetic energy becomes half into m into 2ax, that is max. And we calculate a potential energy at point B is mgh. Here h is h minus x. The total energy at point B is kinetic energy plus potential energy, that is max plus mgh minus x, mgx plus mgh minus mgx. Here mgx and mgx are cancel out and E3 equals to mgh. Hence, E1 is equals to E2 is equals to E3 equals to mgh. This proves that the conservation of energy, because the E1 and E2, E3, 3 are equal to mgh, that means the energy is constant.